this video for Math 10150 Lesson 5, we will be covering systems of linear equations in two variables. So in the beginning of the course, we did equations and just linear equations. And now we're going to do systems of linear equations. So a system of linear equations will look like this. Ax plus by equals c, and another one, dx plus ey equals f. And we're asked to solve the system at the same time. A solution to a system of two equations is a ordered pair of points. Is an ordered pair. x1, y1. In order for something to satisfy the system, it must satisfy both equations at the same time. If it satisfies one but not the other, it's not a solution of the system. And there are three main ways of solving, three methods of solving such a system. And the first method, which may not work all the time, but it's definitely visually appealing, is to graph each one. Remember, each equation in x and y is just a line in the plane. And if you graph each equation, then the solution to this equation will appear at the intersection of the two lines. So the first method of solving such a system is by graphing. Of course, in order to do that successfully, you have to graph very carefully. Another common method of solving them is called the elimination or the addition method. And I'll go over all of these methods. The elimination or the addition method, where you essentially add both equations together or subtract both equations together to eliminate one of the variables, and then you're solving a regular linear equation. Another method is substitution, where you solve one of the equations in terms of one variable and then plug it into the other. And of course, you can use all three methods just to confirm that you got the right answer. And I will do an example, and then I'll go over what else can happen in a system of linear equations where you have zero or infinite solutions. So let's look at our first example. We're asked to solve the following system: 6x minus 3y equals 9, and 2x plus 2y equals negative 6. So we must solve this system. So I will first do this by method 1, by graphing. Again, in order for graphing to be successful, you have to graph very carefully. And I will first have to put both of these equations in slope-intercept form, because as it stands, it's not that easy to see how they're supposed to be graphed. So the first equation is 6x minus 3y equals 9. I'm going to put that in slope-intercept form. That is minus 3y equals minus 6x plus 9, which is y equals to 2x minus 3. I have divided both sides by negative 3. Sorry, there's a minus 9 here. It will probably still work. Okay, so we need to solve the equation 6x minus 3y equals negative 9 and 2x plus 2y equals negative 6. And so we're writing the first equation in slope-intercept form. We get y equals 2x plus 3. Now I'm going to rewrite the second equation in slope-intercept form. 2x plus 2y equals negative 6. So that means 2y equals minus 2x minus 6 divided by 2. I have negative x minus 3 for my second line. And now I'm going to graph them. And in order for graphing method to work, you need to graph very carefully. The first one, I'm going to graph the first one, y equals 2x plus 3. It has a slope, a y-intercept of 3 and a slope of 2. So it's going to look like this. Slope of 2 tells me there's rise over run. There's a rise of 2 for a run of 1. The second line, y equals negative x minus 3, is going to have a y-intercept of negative 3 with a slope of negative 1. So for a rise of 1, there's going to be a run of negative 1. And here I see that there's an intersection of these two lines, and that happens at a point negative 2 comma negative 1. This point is negative 2 comma negative 1. And this is the solution to the problem, the ordered pair negative 2 comma negative 1. You can solve this problem if you plug in x equals negative 2 and y equals negative 1. Now we're going to do this using another method. Now we're going to use the elimination addition method. In the elimination addition method, we write down the two equations and we want to combine them in such a way to eliminate one of the variables. So we have 6x minus 3y equals negative 9, and 2x plus 2y equals negative 6. What I'm going to do is I'm going to multiply there's lots of different ways to do this, but what I'm going to do is I'm going to multiply the second equation by negative 3. And I'm going to rewrite the system. The first I'm rewriting as is, minus 6x minus 3y equals negative 9, and multiplying everything by negative 3, I get negative 6x minus 6y equals 18. Why did I choose to do this? Because now I can add both equations. And when I add both equations, what happens is that I eliminate 6x and minus 6x. One variable is eliminated. And what I'm left with is minus 9y equals 9. So I get that y equals negative 1. Once I got my y, I'm not done yet because I need an ordered pair. That's a solution. I look at any of the two equations in order to get x. For example, the first one, the second equation, the original one, 2x plus 2 times negative 1 must equal negative 6. So 2x minus 2 equals negative 6. 2x equals negative 4. X equals negative 2. I get the same solution I got by graphing, which is a good thing. Negative 2 comma negative 1. Again, this is the solution. This is the ordered pair. That's the solution to this system. And the third method that I'm going to do is substitution. And you can choose any of these two methods to solve unless a specific method is asked for. So method 3 is by substitution. And in substitution, you solve for one variable in terms of the other. So again, I have two equations here, 6x minus 3y equals negative 9, and 2x plus 2y equals negative 6. What I'm going to do is, and there's no rhyme or reason which one you choose, I'm going to take the second equation and solve it in terms of y. So I'm going to take the second equation, 2x plus 2y equals negative 6, becomes 2y equals negative 2x minus 6, y equals negative x minus 3. Notice the same thing that I got when I was putting into slope-intercept form when I was graphing. What I did was I expressed y in terms of x. Now I look in the second equation, so now this is my substitution. And now I go to the second equation and I substitute that in. 6x minus 3y equals negative 9. But what is y now? Y is my substitution, minus x minus 3. And now I expand. This is again an equation of one variable. This is 6x plus 3x plus 9 equals negative 9, which is 9x plus 9 equals negative 9. So we have 9x equals negative 18, x equals negative 2. This is the same thing I obtained in other cases. And now I can plug in x equals negative 2 into my equation for y, and I get that y equals negative of negative 2 minus 3, which is negative 1. So again, my solution is negative 1, comma, negative 2, comma, negative 1. So these are three different methods of solving the same system of linear equations, either by graphing, where you have to graph them, first put them into slope-intercept form and then graph them carefully, or by elimination or the addition method, where you multiply one of the equations by a convenient number in order to eliminate one variable, or by substitution, where you solve one of the equations in terms of the other and then plug it in one variable in terms of the other and then plug it into the second equation. What else can happen with systems is a case of infinite solutions or zero solutions. Sometimes that can happen. The case of infinite solutions is when you are graphing two lines and the two lines are actually the same exact line. So when it's the same line, you get infinite number of solutions. The two lines intersect each other at every single point. Another case, special solution case where you can get zero solutions, is if the two lines corresponding to the two equations are perfectly parallel. If they are parallel lines, then there are zero solutions to the system. So let's see how might these look like. So in example 2, we have the following system. 2x minus 6y equals 12, and 3x minus 9y equals 18. At first glance, they may look like two different equations, but in fact, they represent the same line. So what I'm going to do is, I'm going to do this by elimination addition. I want to eliminate one variable. Let's say I want to eliminate x variable. So what I'm going to do is I'm going to multiply this one by 3, and I'm going to multiply the second one by negative 2, so that I have negative 6x in the beginning. And let's see what's going to happen. The first equation becomes 6x minus 18y equals 36. I have multiplied by 3. The second equation becomes negative 6x plus 18y equals negative 36. And when I try to eliminate, I have eliminated the x variable, but I also end up eliminating the y variable and end up eliminating pretty much everything. When that happens and you have a 0 equals 0, this means there are an infinite number of solutions. The two lines are in fact the same exact line. Another example, how it might look like when you have parallel lines, is as follows. Let's say you have the system 2x minus 6y equals 6, and 3x minus 9y equals 18. Notice this is almost the exact same system as above, except in the first equation we have equals to 6 instead of equals to 12. And I want to do the same thing. I want to eliminate the variable to x, so I multiply this by 3, and I multiply the second one by negative 2, and let's see what's going to happen. The first equation becomes 6x minus 18y equals, this time, to 18. I multiplied by 3. And the second equation is the same as it is in example 2. Negative 6x plus 18y equals negative 36. And what happens now is that I have 0 because the x's cancel, the y's cancel, but instead of equaling 0, I now have it equal to negative 18. And this is complete nonsense. So this means I have 0 solutions. These lines are parallel. So this is something to watch out for. One instance where systems of equations are heavily used, and we'll do one example like this, is an application problem. And the classical application problem with systems is ticket purchasing. So let's say we have some venue, and on day 1, 3 child tickets and 1 adult ticket was sold for $38. On day 2, 5 child tickets and 2 adult tickets was sold for $68. And the question we need to answer is, what is the price of the child and the adult tickets. This is a standard problem, and we would construct our system of linear equations from this problem. So the first sentence says that on day 1 there were 3 child tickets purchased and 1 adult ticket purchased. So this means that 3c plus a equals 38. Notice I have introduced variables here. C is the price of child ticket, and A is the price of adult ticket. And the second line says that on day 2 there were 5 child tickets purchased and 2 adult tickets purchased for a total 68. So now I have a system of equations that will solve me this problem. And let me do this one by substitution. So I can express A as 38 minus 3c. And then I can plug that into the second equation, 5c plus 2 times 38 minus 3c equals 68. So 5c plus 76 minus 3c equals 68. Combine like terms, and you have 2c plus 76 equals 68. So 2c So one common mistake is to not distribute the parentheses properly. So we have minus c plus 76. So we have minus c equals to minus 8, or c equals 8. So the price of the child ticket is 8, and then we substitute that into the expression for A. A is 38 minus 3 times 8, so A is 14. And so that is our final answer. The child ticket was $8, and the adult ticket was $14. And we can check our answer for reasonability, and we can plug in and check that c equals 8 and a equals 14 will solve the problem.